So this is the roster. Remember to write your names on the chat. And then please turn on your web cameras, everybody. Good morning, good to see you all. Energetic and in good spirits to this learning exercise. So it's 11 o'clock. So I think we can start. So first, let me share with you the roster. What is it? Let me see. It's right here. Just briefly. Okay, so this is a roster. So now what? Okay, so you can see the roster now. So we have very good attendance. Congratulations. And then you see that brown fringe, that be next week, Wednesday. I have invited an industry speaker who is going to be in the Zoom. Let me give you a little bit more information about him. So that's, you can see now, Wednesday, February 10th, procurement, design, and commissioning of LED lighting and controller systems. What is his name? Let me see, his name should be over here. Oops. Well, let me put it here. Mr. Tony Nicanor, professional engineer. So Tony is going to speak about procurement, design, and commissioning of LED lighting and controller systems. Okay. So that's next week, Wednesday. Now, this is the roster, okay? We have Mansour in this class. He's a graduate student. He's an instructor, and he'll be taking care of your roster and also grading. So he's going to help grading. Okay. So now let's see, what do we have for homework? 6Q. This was due last Saturday. So now we will jump when we get to chapter 6, which be Wednesday. We'll talk about this homework. Problems and readings. The usual pattern, we'll read chapter 6 questions, homework 8, and we'll do numerical problems, homework 7P, chapter 6, and here are the problems that we are going to do. But they are not on Blackboard yet, okay? So you don't need to worry about that now. Fine, so this is the okay. So now let's let me Let me open this. Can you see the chapter 5, lighting systems, layout and interior spaces?
Yes, we can see it.
Okay. We will be able to determine the lighting level recommended for a specific task, calculate the required number of luminaires, prepare a plan, actual arrangement of luminaires, do an economic comparison between lighting systems, factors involving the quality of light. Introduction. The design of a lighting system for an interior space involves many variable factors. Okay, so let me move on. Hold on. Okay, so the areas are classified according to activities, and therefore, where is it? Let me show you from the book. I think I showed you this the last class. Right here. Okay. So you can see my web camera on my desk. So according to lux ranges, we have the different area or activities. So these are luxes. Remember to convert luxes to foot candles, divide by 10, and that give you an approximation. Okay, so then for any given area, we will have a minimum amount of illumination. Okay. Okay, the lumen method. So this is what we want to do. Look, I draw this conceptual map of illumination transport. I use the word transport because here on top we have the source in lumens. So this is emitting radiation in red arrows upwards in every possible direction according to the pattern. And then we have a wall, we have a cavity like the room, okay? And then at the bottom, now we focus our attention on the work plane. So we want to determine the illumination received on the work plane. So that illumination is going to be given in luxes, lumens per square meters, or equivalently foot candles, which are, lumens per feet square. Okay. So we want to find out the illumination dot here, and that is this equation. Now go to in the shared document, E, the total luminous flux falling on the work plane divided by the area of the room. That's going to be luxes, this E. Okay, so this is what we are talking about. E here equals, all right. So that's the general definition. Now we need to consider, now we have this equation, phi 1. So let's look at what that equation entails. So we have TILL, total lamp initial lumens. Okay, TILL means the total initial lamp per lumens. Total initial lamp lumens, which is total lamp multiplied by initial lumens per lamp. Now, there is a coefficient of utilization, which is given by this ratio of the total initial lamp lumens, what percentage arrives in the work plane. See, because...
Dr. Ramos?
Yeah.
I've taken the attendance. Do you want me to stay or?
No, it's not necessary if you want to stay.
Okay, then thank you, Dr. Ramos.
Send the...
I've sent you the roster. I've sent you the roster. I'll be leaving now.
Okay, thank you. Fine. Coefficient of utilization. All right, so that's the percentage of lumens that arrives in the working area. It's going to be complicated. Let's see. It depends on the type of luminaire. It depends on the reflectance of the room surfaces. Okay. Next, oh, poop. I don't know why I don't see, I cannot scroll to the next. Okay, so. See one. Okay, next. It depends on the geometry of the room. For example, in if we have an initial room with 200 square feet, 20 times 10, and we length the area of the room, we put two more luminaire. Then in the middle diagram, we see that those two luminaires are very far away. So the lumens per square feet arriving at point A from the far luminaires is going to be smaller than if the increase, now alternatively, the doubling of the area is done in the bottom diagram. Instead of growing, elongating the area here, the area goes on square. Now the two luminaires are much closer, so therefore the coefficient of utilization is going to be larger for the bottom figure than from the top figure. So it depends on the, okay. Now, what's going on in the cavity? So in order to do the analysis of the cavity, we can have this general picture where we show the work plane on the bottom and the luminaires on the top. And then there are going to be three cavities. The ceiling cavity above the luminaires, the floor cavity under the work plane, and then in between the room cavity. So we are going to have three cavities, okay? Now, we have reflectances, ceiling, floor reflectances, wall reflectances. So there are three reflectances. Now, we have dimensions, h, which are heights of the ceiling cavity, of the room cavity, of the floor cavity, okay? Fine. So now we are going to define, now let me look at, we are going to use a lot of acronyms. So here I'm putting the acronyms. Okay, so we are right here. Coefficient of utilization, and then the cavity ratios. Now we are going to define the cavity ratios. So it depends on, let me see, the definition is right here. The cavity ratio is 5 times the height. And then we have this geometrical area, room width plus room length. Okay, so I put that as this simplified formula. So a typical length, which is like the parallel formula, the parallel resistance formula, but now using here length and width of the room, okay? So therefore we have three cavity ratios, one for ceiling, one for room, and one for floor. And here are, in this example, we have these calculations, okay? So they are very simple. So I brought this to do the calculation. Okay, so for example, if 100 times 100, so the area is 10,000, the L equivalent is 50, like the parallel. Okay, so then we have 5H divided by 50, and then H is going to be 20 feet. So therefore this is equal to 2. 5H divided by 50 is equal to 2. Okay, so that's the example 1 for room cavity. Now another example. Now this is going to change. 40 times 250 over 290. So this is the equivalent resistance formula, okay? So LC, this is going to be, then we multiply 5 times H, again 20 divided over, so let me, I need my calculator, hold on. Okay, so 40 times 40 times 250 divided by 290. That's 34.5 times 100, 2.9. Okay. See, the surface area are the same, 10,000. However, the cavities ratio are different. Okay. Now in the bottom example, now this is a different room. Okay, so let me forget about that. Okay, so we were calculating cavity factors as shown here. Okay. Now the next topic is wall reflectances. So we have two types of reflectances in the wall, and now we have what is called base reflectance. So base is going to be ceiling or floor reflectances. Ceiling or floor reflectances. And now we have something which is called the effective ceiling or floor reflectances, which are given in table 5.4. So let's move forward. See here, look at the table, okay? Table 5.4, effective cavity reflectances. So we use base for either floor or ceiling. Okay, now wall is going to be from 0 to 90, from 0 to 90. Next, we have here 0.2 cavity ratios. Look, we have cavity ratios from 0.2 to 10. And then we get all these numbers, which are given by effective cavity reflectance. Okay. So we choose the wall reflectance, and then we choose the cavity ratio, and then we are going to calculate the effective cavity reflectance. So let's move to the next. Okay, so then let me show the next example. The next example is here. Okay, so it says a room is 60 times 120, 24 feet high ceiling. The luminaire when in table 5.5 is used, suspended 5 feet below the ceiling. The reflectance factors in ceiling are 60%, wall 30%, floor 10%. The work plane is 3 feet. Calculate the coefficient of utilization. Wow. Calculate coefficient of utilization. So this problem looks complicated. So here are the geometry. Look. Okay. So here is the geometry. So first calculate the cavity ratios. So they are calculated here. 5 times. This is ceiling. So there are 5 feet. 5 feet here, look. 5 feet here. Okay. For ceiling, so that's the H. Then for room, 16 feet height. That's this 16 here. Then for floor, the floor is 3 feet height. So that's this room, this number here. Next, the parallel resistance formula, which would be length or width and length, 60 and 120. So they are the same for all of them. They are the same. So therefore, we get these numbers, 0.6, 2.0, and 0.4 for the cavity ratios, okay? Cavity ratios. Now, we need to get the coefficient of utilization, okay? That's what we are going after. Coefficient of utilization. Okay, so that's, once we have the cavity ratio, the next is determine the effective ceiling cavity reflectances from table 5.4. Table 5.4, it's you can see table 5.4 there. Okay, so it's going to look at that table. So let's read carefully what it says. For a base reflectances of 60%, wall reflectances 30%, and cavity ratio of 0.6. Base, okay, base 60%. So that be on the right, the 1, 2, 3, 4, 5, 60. So the second to last on the right, that's the base. Okay, then what else? Base 10, wall 30, wall 30, and cavity. So now pick up 30, and then cavity ratio go down to 0.6. 0.6, so that's the third row, and then I see 51. Row CC equal to 51, use 50. So that's step 3. I cannot point on the table. I don't have a marker for that, but that's the table we will use. Then step 4, so that's ceiling cavity, now floor cavity. So now for base is 10%. So now you go to the bottom part of the table, find 10% for base reflectances. We are in step number 4. Wall reflectance 30%, cavity 0.4, 10, and then cavity 0.4, and that is 0.09. 0.09, and then 10% did not change. So that's step 4. Then step 5, determine the coefficient of utilization from table 5.5. So now let's move to the next table. Look at this. This is a very interesting table because now it depends on the luminaire. So then look at the, let's look at this table, look. It's got 4 different luminaires. Okay, typical luminaire. Then the second column, it says maintenance catalog. So there is a 4th, 5th, 2nd, and 3rd. So that's the maintenance catalog with Roman numerals. So that is the light source information. Then we have SC. And then we have the radiation pattern. The radiation pattern, look. Okay. How do we call that radiation pattern? Distribution, right? We called it not radiation pattern. It was called, from last chapter, it was called, from chapter number 3.
Intensity distribution curve.
Yeah, the intensity distribution curve. Okay. And then next column, I don't remember right now what SC means. Let me see. I have my I didn't put it here. My acronyms. Okay, we'll find out in a moment. Okay, so then next is the room cavity ratio here, that column. And then we have the coefficient of utilizations, all these numbers in percent. And then on top, the very first row, we have the reflection coefficient of the CC and wall. Okay, so we have reflection coefficient of wall. Okay, and then we have reflection coefficient of cavities. No, ceiling. On very top, the ceiling. The ceiling, 80, 70, 50, 30, 10, 0. And then we have this note, coefficient of utilizations for 20% effective floor cavity reflectances. For 20%. Okay, so this is for that. Okay, so then coming back here, we have step 5. Determine the coefficient of utilization from table 5.5. For luminaire type 1, the reflectance of ceiling is 50%, the reflectance of wall is 30%, the room cavity ratio of 2, the utilization is 0.67%, 0.67, not percent. So this is luminaire number 1. So then room cavity ratio is number 2. So it's going to be the third row. And then move to wall 50, 30, no, now ceiling. Ceiling is 50%, okay? So is the middle large group column. And then 30. So I see number 67 right there. Right there, number 67. So that's what it says here, doesn't it? Yes, 0.67 for 20% reflectances. But it is not 20% reflectances, it's 10% reflectance. So then it says that 0.67 has to be modified according to the next table, which is table 5.6. Other than 20. So we are in effective ceiling cavity reflectance. Ceiling is 10. So we go to the last column, 10. And then the wall reflectance, we said it was 30. And then the room cavity ratio was 2. So here I have 1.01. And in the bottom, I have 0.991. So what it should be? It should be 0.968. What is it? Wall is 30. I'm lost. Okay. So 10% floor reflectance, CC 50% or 50% here.
Second entry, right above. Yeah.
9.68. Okay. So as you can see, this is a complicated task, okay? Because this is only the beginning numbers. Fine. Okay, so Mr. Nicanor is going to tell us how does he design and sells his projects. Does he use this type of information? Okay, so that's example 5, which said the following. Let's read again the example. A room is 60 by 120 in the area of 24 feet high ceiling. The luminaire 1 in table 5.5 is used. It is suspended 5 feet below the ceiling. So that's the ceiling cavity. The reflectances factors are ceiling 60%, walls 30%, and floor 10%. The work plane is 3 feet above the floor, and then calculate the coefficient of utilization. So look, this is just the data that we were given. We were given the reflectances and the room and the areas of the cavities. That's all. And calculate the now the final coefficient of utilization is going to be 0.65. So that means, look, according to this formula, that of the foot candles, the illumination on the work plane is going to be given by the total initial lamp lumens, multiplied by that 65% and divided by the area. Okay, so that's the value of the example 5.5. So now let's do the next example. It's going to be 5.6. Let me see where I have the examples. Okay, 5.6 right here. Okay, luminaire 3 is used for a lighting layout. The atmosphere will be clean, and the period between cleanings will be 24 months. Determine the LDD. Okay, light. Let's see what LDD is. So here is my, okay. All right, so look, after calculating all those coefficients, the next topic is the light loss factor. So we have different factors affecting the light. So the LD is the lamp lumen depreciation. The LDD is the luminaire dirt depreciation. So in this case, it is asking for LDD, the luminaire dirt depreciation. So all these factors, this is a ballast factor. The ballast is the electronic device, the interface between the source and the lamp. So some energy is lost there. So that's why it comes here. Then we have lamp lumen depreciation. This factor is after some years, the lamp does not emit the same number of lumens. And then the luminaire dirt depreciation, and then the RSDD, which is the room surface dirt depreciation. Okay, so then these last two have to be maintenance also. Okay, so let's see what it says. Table 5.5, the assigned maintenance category for luminaire 3 is number 2. Luminaire 3, okay, so table 5.5. So let's go to table 5.5, right there. So we are talking about luminaire 3, which is this industrial fluorescent right here. So maintenance category is second, Roman numerals. Okay. From figure 5.4, category second graph, for clean atmosphere at 24 months, the luminaire dirt depreciation is 0.89. Figure 5.4. So what is figure 5.4? This is let me see. Where is figure 5.4? Excuse me. Let me bring the figure 5.4. Wow, there are a bunch of figures here. Let me see if I can bring it up. Figure 5.4 right here. No, not table, figure. Sorry. Right here. So this is the figure, look. Look, so therefore we are second category here. Then we have different plots, different graphs. So BC, very clean, medium, dirty, and very dirty. And then the months. So in this case, it says that clean atmosphere and 24 months. So that's this graph and clean. So it's a little bit under 0.9. So it's maybe 0.88, 0.88. Okay, so it gives 0.889. So that's going to be a luminar dirt depreciation. Okay, luminar dirt depreciation. So that's example 5.6. So let's go to the next example. 5.7. Luminar 3 is to be used. The atmosphere will be clean. The period between cleanings will be 24 months. That's 2 years. The room cavity ratio has been calculated to be 2.0. Determine the room surface dirt depreciation. So now that's on the room surface dirt depreciation. So that's on the walls, okay? Now table 5.5. So table 5.5, let's see where that is. Here is table 5.5. Luminaire has a ratio of 22.5 to 65% for upward and downward light components. So which is luminaire? 3. So it says these numbers here, 22.5 and 65, which translate to 26 upward and 74 downward. We are looking at number 3. So some radiation goes to the ceiling, and the majority of the radiation is projected downwards. From figure 5.5, the luminaire is semi-direct type. From the graph in table 5.7, now we need to find table 5.7. Hold on, table, I need to find table 5.7. Page 158. Let me find it here. I don't have it in. Okay, so this is table 5.7 here. And so these are the room surface dirt depreciation factors. Okay, so I lost track of this exercise. I'm sorry. I cannot follow it now. So anyway, the idea here is to calculate the total light loss factor, which is all that multiplication. And therefore, the formula for foot candles, for the illuminance, now is going to have that factor, light loss factor right here. The original formula was, so we started with TILL, which is total initial lamp lumen, TILL. We started by that divided by area. Next, we added the coefficient of utilization, right? The coefficient of utilization coming because in a manner to describe this transport of lumens to the work plane being affected by the wall and the cavities. So that's the coefficient of utilization. And then next, what the book is describing right now is this light loss factor, which is due to maintenance, dirtiness, etc., etc. And then we calculate this total illuminance in foot candles. Okay, next is going to be the number of luminaires. So now the number of luminaires is going to be given by the total initial lamp lumens divided by the number of lamps and the initial lumens per lamp. So now the next topic is going to be how are those luminaires distributed in the room. So then this is example 5.6. Let me see, now this one. Where is it? Well, here is a calculation for the total lamp lumen depreciation, lamp lumen loss factor here. And here are all the factors: look, ballast, lamp lumen depreciation, okay, LLD. Look here, lamp lumen depreciation and luminaire dirt depreciation, and then room surface dirt depreciation. So then all these factors combined, they bring the light loss factor to 64%. The lighting level will be reduced to 64% of the initial level just before corrective action is taken. Okay, so corrective action is mainly maintenance, cleaning, changing lamps. Okay. So that's example 5.8. Then example 5.9 is the same room, coefficient of utilization 0.65, luminaire 1, a how many watts? Mobile base, 1000 hours, incandescent lamp. So now it's talking about the lamp itself. Okay. Foot candles. The atmosphere will be clean. The luminaires and room surface will be clean every 18 months. Calculate the number of luminaires required. So now he's going to use number of luminaire requires according to this formula. Okay. The lamp lumen depreciation factor from table 4.1 is 89%. The luminaire depreciation factor from table 5.5 is 1. Category 4, figure 4, the clean 18 months lamp depreciation factor is 0.84. Determine the room surface dirt depreciation factor from those graphs. Dirt depreciation is 50%. Light loss factor 0.73. Total initial lumen. So these are the 60 times 120. So that's the area. 20 is the number of foot candles. And then on the bottom we have light factor and lumen depreciation. So the total initial lumens needed are 303,500. That's the total initial lamp lumens. Calculate the required number of luminaires. So now he's going to divide that by the lumens of the lamp. So we are talking about one lamp of 5,960 lumens, and the total is 303,500. So therefore, 51 luminaires are needed. Okay. 51 luminaires are needed. Okay. Wow. So it's been a difficult class, this one, huh? Because it's a complex topic. All right. So therefore, then the next example is going to be about the layout. So 50.9 incandescent luminaires to provide an average level of illumination of 20-foot candles for a 60 by 120 foot room. Select a practical layout for the lighting in this room. So let me see if we have some figures before discussing the problem. Let me look at the laying. That's 164. Okay, so I think it's no, I don't have it. Figure 5.9. So that's the way he depicts distribution of lamps. So here we have, let's see, 1, 2, 3, 5 rows, and then there are going to be 10 luminaire per row, 10 luminaire per row. Regular spacing, look. So the separation along the length is equal to the separation between rows. Okay. Here is another figure regarding so the symbols that are used. So this is a spacing, vertical spacing between rows, and then horizontal spacing between columns. And then the idea is to have those spacings approximately equal. Now there are some other cases, for example, in this design where continuous rows of fluorescent lamps. Okay, fine. So here is discussing this problem, 510. So now 60 by 120, and so he needs to distribute 50 lamps in a 60 by 120. Okay, so then the spacing is going to be 12 foot. Okay, now here is a new concept which is given by the actual maintenance. This calculation is, instead of 20, is going to give foot candles a little bit less. So here the calculations involve these variables: the length of the room, the width of the room, the luminaires per row, or equals to the number of columns, the number of rows, and therefore the separation between columns along the length, and then the separation between rows along the width. So I'll try to have regular spacing. And then once the layout is determined, the next topic is going to be to calculate the power. So from table 4.4, let me show you table 4.4. Right here. So table 4.4 is for fluorescent lamps. And then we have different type of lamps. And then see each of them is described by the current of the lamp. So I think he's talking about the 1500 milliamp. And then right here we have input in watts to the ballast. So for this example, he's going to use 450 watts. So that's a heavy wattage ballast. Okay. This is for high intensity lamps. Look. Again, also the number of watts to the ballast. So these are the industrial type of lamps or the outdoors lamps, okay? So in this example that we were looking at, no, sorry. Right here, to get the total power, we get the number of lamps times the input power, and then one benchmarking quantity is the unit power density divided by the area. And this total power in the lamps divided by the area becomes a benchmark, because we must not go over a given amount of watts per square foot, okay? So in table, let me see, example 511, he calculated 75 luminaires, the same 60 by 120 feet room is now to be lighted up to 11 of 75 foot candles. Luminaire number 3, and then the cavities, now the 800 milliamps. The okay, select a practical lighting layout. Example 511. So that's the layout he determined. Okay, and then he calculated the spacing. So all those are the formula for spacing. Okay. Well, I'm going to stop here. I could not have more participation. It took me a lot of time to describe. I wanted to transmit to you the idea of how involved is this design. And fortunately, we now have computer methods, right? Remember that, let's see, hold on, let me, what do we have for lumen method? Remember we were looking at www
Visual 3D.
visual 3D.com. Right there. And then we go to interior. Okay, so see here are the reflectances. Then the criteria, look, here is the power density that we were talking about. The quantity, we don't have a number of luminaires, foot candles, quantities. We have not chosen a luminaire here yet, so for that we must use this plus sign. And then after we play with the number of luminaires, the type of luminaire that we want to select, the calculation results are going to be shown on the right. So we are going to be given foot candles and power density, watt per square foot, and then also spacing, arrangement, etc., etc. So this software should be, I want to go back, okay, escape, no, okay, fine. So thank you for your attention. I hope it did not become too boring to you, but I wanted to go through some of the detail to transmit the idea of this engineering design method. Okay, so please, I already have you already have a roster, so I checked your names on the roster. So if somebody did not write on the roster on the chat, then do it now, and this time I will dismiss the class. Thank you very much, and see you on Wednesday.
Thank you, Dr. Ramos.
Bye.
Yes.